Main idea here is we're going to be talking about something called a differential equation. A differential equation in x and y is an equation that has x, y, and derivatives of y. A solution to a differential equation is a function that satisfies the differential equation when the function and its derivatives are substituted into the equation. A solution to a differential equation could be one function, a singular solution, or a set of functions called the general solution. So as you can see in the box, you can use y prime, dy dx, and it can be the second derivative of y as well. So let's look at example 1. A particle moves along a straight line. I'd like you to use your highlighter. Its velocity is inversely proportional to the square of the distance s it's traveled. So which of these four would describe that relationship? So discuss at your tables. 10 seconds, real quick. What do you think? All right, well, let's do a little process of elimination. When it says velocity v, that immediately eliminates two of the four choices. Which ones does it eliminate? C and D, right? Because it's not a derivative. It doesn't say a rate, okay? So that's our first elimination. Then it says inversely proportional, and then in the green box I'm going to go over, what's direct variation and inverse variation. But it's inversely proportional to the square of the distance, so if you said letter choice B, you are correct. So here's a quick refresher from Algebra 1 and Algebra 2. Direct variation occurs when a situation gives rise to a linear function, f of x equals k times x, where k is the variation constant, or constant of proportionality. We would say y varies directly as x, or y is directly proportional to x. So there is this constant of variation that's included. That's what the k is. Inverse proportion really is the rational function situation. So it's where y equals k over x, and we would say y varies inversely as x, or y is inversely proportional to x. So then let's look at example 2. A puppy gains weight W at a rate. So now do you see I've got a rate approximately inversely proportional to its age t in months. Write an equation that describes this relationship. So I would say dw dt equals k over t, because it was inversely proportional. All right, example 3. The learning rate for a skill S is proportional to the difference between the maximum potential for learning that skill, capital M, and the amount of that skill already learned, L. We want to write an equation that describes this relationship. So it's the learning rate. So I'm going to do ds dt. And it is proportional, so it's not saying inversely, so that's automatically directly proportional to the difference between the m minus the L. So what's really kind of cool as we're going through these, do you see the different areas of application at the same time? So in chapter 7 and 8, we're going to get the punchline, okay, for why we were learning all the integral techniques, okay? Example 4. An IV drip administers medication to a patient's bloodstream at a rate of 3 cubic centimeters per hour. At the same time, the patient's organs remove the medication from the patient's bloodstream at a rate proportional to the current volume V of medication in the bloodstream. Which equation describes this relationship? All right, so think about this one. All right, discuss at your table. What do you think? So you have the IVs dripping, so that's going in, and then you have something that's being removed at a rate proportional to the current volume. So what do we think? I'm hearing a lot of different answers. So can we agree it definitely couldn't be B? Okay, it definitely can't be B. Because you're putting in at 3 and then subtracting off your volume. So then it's actually not C, and it's actually not D, it's letter A. So you're putting in just at a flat rate of 3 and then subtracting at a rate that is proportional to the volume. So that was letter choice A. All right, let's try another one. Example 5. A chemical is diluted out of a tank by pumping pure water into the tank and pumping the existing solution out of it. So the volume at any time t is 20 plus 2t. The amount Z of chemical in the tank decreases at a rate proportional to Z and inversely proportional to the volume of solution in the tank. So I don't want you to get distracted with this pumping the water in and out, because I've just given you what the volume is, okay? The volume at any time then with all that happening is the 20 plus 2t. So then the amount Z of a chemical in the tank decreases, so that Z somehow has to be negative, and it's inversely proportional to the volume. So can you see that that's going to eliminate C and D, because inversely I need it to be underneath. And then now we can eliminate choice B because it's decreasing at a rate proportional to Z. Okay, so that's letter choice A. All right, then there was an example that the teacher did this thing about coffee, and I'm like, I don't drink coffee, so but my husband loves coffee, so I thought I'll just throw him in there. Here's example 6. Mr. McInerney despises lukewarm coffee, so he makes extra care to make sure his coffee stays hot as long as possible. He is convinced that the first few moments after pouring his coffee are critical, but he wants some solid proof. Does calculus have any answers? Let's find out. The rate at which the temperature of coffee changes can be modeled by dC dt equals 0.054 times the quantity 70 minus C. So dC dt is the rate at which the temperature of the coffee is changing over time, where C represents the temperature of the coffee in Fahrenheit, and T is measured in minutes since the coffee was poured. So in part A, it says how fast is the temperature of the coffee changing when the coffee is first poured at a temperature of 185 degrees. So because we're going to do this twice, you're going to need a calculator, so grab your calculators. And something while I'm letting you grab those, do you notice by the equation that dC dt is proportional to the current temperature of the coffee. Like this is what that equation is saying. So when C is 185 degrees, we want to know how fast is the temperature changing. So that is the derivative. And remember to include units. So I got negative 6.21, and I would say that's degrees Fahrenheit per minute. That's the rate it's changing. And really, doesn't that mean it's cooling down, right, the coffee? So immediately, now do how fast is the temperature of the coffee changing when the coffee is 170 degrees. All right, what do we get? Have you got it? Elizabeth, you got it? Good job. Negative 5.43 degrees Fahrenheit per minute. All right, soon in this unit, we're going to learn how to go from, and really we know how to do this already, we'll be able to figure out how to go from dc dt to doing that antiderivative to get c of t, which is 70 plus 115e to the negative 0.054 t power. What is c of 0? Now you actually can do this one without a calculator, because what is e to the 0 power? 1. So that's 70 plus 115, which is 185. What does this represent? Yeah, at time 0, or couldn't we say the initial temperature of the coffee when it is first poured? In the next part, I want you to find the derivative of C of T. We're going to do that with your derivative techniques that you know. And this particular problem could be like a free response style question. So we know the derivative of a constant is what? 0. And so then I'm going to have the derivative of e to the stuff times the derivative of the stuff. So I said that was about negative 6.21 e to the negative 0.054 t power. Oh, so now when we looked at that dc dt at 185 degrees, which was the initial pour, don't we get the same thing there? That's kind of cool. All right, now it says we want to show the answer that we got in part C really is the same thing. And let me show you how we're going to do that. pull this back up. So if I have dc dt was 0.054 times 70 minus c, watch what we can do. We can substitute that c was the 70 plus 115 e to the negative 0.054 t power. So all I've done is I've taken what they gave us up here. I'll bring that right back, but I'm taking this one and I'm plugging in what c is. So the 70 minus 70 cancels, and then I do have to distribute that minus sign, and look what we get. We do get the same thing. So it's kind of interesting to see two different forms for that derivative. That's going to play out for us in this unit. It'll make a lot of sense. All right, then, and again, this is an excellent free response style question because you see I've done derivatives, and now I'm going to look at a limit. It says, find the limit as t approaches infinity of c of t. Well, do you see? This is like really, really fantastic stuff. So this is the limit that I'm looking for. So if I have e to the negative exponent, do you remember what e to the x looks like? So this is, I do this, I do arms all the time in algebra too. So this would be e to the x, right? If I do negative e to the x, it looks like this. So as x is going to infinity, what does e to that negative exponent go to? 0. So then this is 70 plus 0, or 70. What does that mean in the context of our problem? Yeah. Okay, awesome. That's the room temperature, but what about the t goes to infinity? Can we like put it all together? You're right, that's the room temperature. But what does t go to infinity really mean realistically? Okay, the longer you leave it out, the coffee will reach room temperature. Now it's not going to get colder than room temperature, right? Okay, so let's kind of interpret that because they would probably ask us that. So after a lot of time has passed, the temperature of the coffee will cool to 70 degrees, the temperature of the room. So they like to do that on the AP exam, ask you to like interpret your answers. All right, and because 7-1 was so short, we're doing 7-2 because it's also short. Tomorrow is the ACT. Juniors will be taking that. Seniors, you can just work on this 7-1, 7-2 homework. So seniors just get a little extra time. All right, so in 7-2, we talked about this at the very beginning, that a solution to a differential equation is a function that satisfies the differential equation when you plug it back in and its derivatives back into the equation. So if we look at example 1, it says determine whether the given function is a solution. Determine whether the given function is a solution of the differential equation f double prime of x minus f of x equals 0. So what we're going to need to do is we're going to need to find the first derivative, and we're going to find the second derivative. And then what you're asked to do, it says determine whether the given function is a solution of this differential equation, f double prime of x minus f of x equals 0. So I'm going to take negative sine x minus sine x. That does not equal 0. So no, f of x equals sine x is not a solution to f double prime of x minus f of x equals 0. So what I'm going to do is I'm going to pause a moment, and I want you to try letter B and C. You're going to need to find the first derivative and the second derivative, just like I did. So you got some chain rule happening. And then plug it in to f double prime of x minus f of x and see yes or no. Is it a solution? So this will be good practice. Yeah, so in part C, that C is in fact a constant. And the way that you know that is it's f of x. So then any other letter is going to be a constant. All right, for letter B, did you get yes? Yes, yes, yes. Be careful with that little chain rule. And then did you notice part C, this was not very interesting, right? Because f prime is c e to the x, all the derivatives would be that. Okay, so now let's look at example 2. It says determine whether the given function is a solution of the differential equation dy dx equals 4y over x. So y is 4x, and then do you understand that dy dx is just 4? So I want to know, then, if I go to dy dx equals 4y over x, well, dy dx is 4, and then I would have 4 times 4x over x. The x's cancel, but that 4 does not equal 16, right? So that's a no. All right, try letter B on your own then. if you can see what I did there. All right, what do we get, yes or no? Yes. So let's figure out how. dy dx is 4x cubed. Then I'd have 4x cubed, and does that equal 4 times x to the 4th over the x? And the answer is yes. All right, go ahead and I'm going to give you a head start on example 3. See if you can figure this one out. For what values of k, if any, is y equals e to the 2x plus k e to the negative 3x a solution to the differential equation for y minus y double prime equals 10e to the negative 3x. So what do we know about k in the problem? It's a constant, okay? All right, so let me give you a few minutes and try this one. And once we finish this problem, I'm going to pull up that worksheet after the Chapter 6 test. I did some implicit differentiation just to get that back in your brains. And then I tackled Rolle's theorem and mean value theorem again because we struggled with that. And then I put some limits. And then I had a nice free response question practice, and that would have helped before the test. And I want to go over that one as well. In case you're having difficulty getting started, your first step would be to find the second derivative. So let's double check before you go any further. Did you get y double prime is 4e to the 2x plus 9k e to the negative 3x? Did we get the second derivative correctly? All right, awesome. So then what you're going to do is we're going to go plug in to 4y minus y double prime, and we want to know if that's going to equal 10e to the negative 3x. Well, y is e to the 2x plus k e to the negative 3x. Be careful to distribute So my 4e to the 2x cancels. So then you're coming down to that negative 5k equals 10. So k equals negative 2. How many got that? You guys get it? Awesome.